You ever wonder how your phone just knows how to find every single picture of your dog? Well, it's not magic. It's something called computer vision. And today, we're going to break down how it all works. We're drawing from research material by Dr. Sudheendra S G, specifically to help you, as educators, get a real handle on this incredible technology so you can explain it too.
And this quote right here, it really gets to the heart of everything. See, a camera can snap a photo, but that's not the same as seeing. The real trick, the entire goal of computer vision, is to bridge that gap, to go from just capturing a bunch of dots to actually understanding what's in the picture.
Okay, so where do we even start? How do you teach a machine to perceive the world? Well, you have to start where the computer does. We've got to peel back the layers of an image and get right down to its most basic, fundamental building block. And here it is, believe it or not, every beautiful, complex photo you've ever looked at is, to a computer, just a giant grid of numbers. Each number represents one tiny little dot, a pixel, with its own color or brightness. That's it. That's the whole foundation. Pretty simple, right? But, a single pixel on its own is kind of meaningless. It's like one letter in a whole book. It doesn't tell you the story. To find something useful, like, say, the edge of a face, a computer has to look at how pixels relate to their neighbors. It's got to see them in little groups or patches. And this is where the magic really begins. We use this tool called a kernel. Now, you can think of it like a tiny magnifying glass, but it's a special one. It's been designed to hunt for just one specific pattern, like a vertical line or a sharp corner, and nothing else. So we have this little pattern-hunting magnifying glass. How does it actually work? Well, it uses a process with a fancy name, convolution. I know, it sounds complicated, but I promise you the idea behind it is actually super straightforward. It's really just a simple repeating dance. You place the kernel on a patch of the image, then you multiply the numbers that line up and add them all together to get one new number. You write that number down, then you just slide the kernel over one spot and do it all over again across the entire image. Now check out this specific kernel. Look at how it's built. Negative numbers on the left, positive on the right. This design is really clever. It means the only way it's going to produce a big score is if it lines up perfectly with a spot in the image that goes from dark to light. In other words, it's a perfect little machine for finding vertical edges. And boom, here's the aha moment. On the left, you have the original messy grid of pixels. But after our little kernel scans over it, look what we get on the right. All the other junk is gone, and only the strong vertical edges pop out. We've literally filtered the image down to its basic skeleton.
Now, for years, this was a really slow process. Experts had to sit down and design every single one of these kernels by hand. One for vertical lines, one for horizontal, one for curves. You get the idea. But then someone asked the big question. What if the computer could just figure out the most important patterns all by itself? That question changed everything. And this slide shows that massive leap. On the left, you've got the old way, these classic methods that used rigid, hand-coded rules. And on the right, you have the modern way, convolutional neural networks, or CNNs. Instead of being told what to look for, a CNN learns what patterns matter by looking at thousands of examples. It's the difference between just following a recipe and actually becoming a master chef.
Now, this is the key idea for your classroom. A CNN learns in layers, kind of like a person does. The first, early layers, learn to spot really simple things, like basic edges and blobs of color. Then, the middle layers combine those to see more complex stuff, like corners and textures. And finally, the deep layers put all those pieces together to recognize a whole object, like an eye, a nose, or a complete face. It builds understanding from the ground up.
So, now we have a machine that can teach itself to understand an image. The next question is, what do we do with that power? This moves us from the how to the so what, from the mechanics to the real-world applications, and, well, the big responsibilities that come along with them. So at a high level, there are two main things we ask a computer to do. The first is classification. That means looking at the whole picture and giving it one label, like, is this a picture of a cat? Yes or no? The second is detection. This is about going deeper, finding where things are in the image and drawing a box around them. Not just there's a cat, but the cat is right here. Okay, but how do we know if the computer did a good job? How do we grade its work? For that, we use a score called intersection over union, or IOU. It's really just a smart way of measuring how much the box the computer drew overlaps with the actual correct box. A perfect score is 1. A total miss is 0. Simple as that. And this brings us to probably the most important part of this whole conversation. Because once a computer can see, we start to rely on its judgment for real decisions. So what do we, as the people building and teaching about this stuff, need to be responsible for?
Well, for one, these systems are only as smart as the data we give them. If you only show it pictures of golden retrievers to teach it what a dog is, it's going to have no idea what to do with a poodle. That's bias. Then there are huge questions about privacy and consent. And finally, these systems can be surprisingly fragile. A model that works perfectly in a bright lab might totally fail on a foggy day.
The good news is we have a toolkit to build this stuff responsibly. We can actively test for those blind spots and biases. We can be transparent and make sure people give clear consent. We can design systems that protect privacy by keeping data on your device. And, maybe most importantly, for any critical decision, we have to make sure there's always a human in the loop. So that's the whole journey, right there. We start with simple pixels, the computer finds patterns, and those patterns lead to decisions. It's an incredibly powerful pipeline that's already changing our world. And it leaves us with this final thought. The most important feature we can build into these systems isn't just making them accurate, it's making them responsible, right from the start. Thank you for watching.